Okay, so in this video we will study the symmetries of a perfect square. And by symmetry of perfect square, what is meant here is the sets of all rigid motions that map vertices of this perfect square, labeled as 1, 2, 3, 4, onto other vertices of a given perfect square. So as a starting point here, let us consider this motion. We will take this perfect square and we will rotate this perfect square around the origin of the plane by 90-degree counterclockwise. So notice what's going to happen is now 1 is located here, 2 is here, 3 is there, and 4 is here. Let us try to write down exactly what just happened. Okay, notice that under this map, what happened is when we rotated the plane around the origin by 90 degrees, we call this R, this map R. Then 1 is now located in the second corner. The vertex 2 is now located in the third corner. The third vertex is now in the fourth corner, and the fourth vertex is located at the first position. So this rotation can then be represented by the function. You can think of this rotation R as a function which is mapping the set containing 1, 2, 3, 4 into the sets containing 1, 2, 3, 4. And 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1. All right, let us now look at the map which will rotate again the square around the origin of the plane by, let's say, instead of 90 degree, we'll go to 180 degree. Now, let us summarize what just happened. Now, so what just happened is the following. We can think of a counterclockwise rotation. One can regard a counterclockwise rotation around O by 180 degree as a counterclockwise rotation around O by 90 degree composed with itself. So in other words, we are taking the rotation which we defined earlier, and then we're composing that with itself, and we can denote this as R square. And R square can then be regarded as a function which takes the set containing the number 1, 2, 3, 4 to the same set, and it acts by mapping 1. Notice that the first vertex now is now located in the third corner. The second vertex is now located in the fourth corner. The third vertex, you can see here, is now located in the first corner, and the fourth vertex is in the second corner. So we can think of this map R as this function which we just represented here. So that's another symmetry which is obtained again by composing our first rotation with itself twice. Now let us rotate the square around the origin by counterclockwise by 270. So this is what we get. Now let's try to write down what this map is. All right, so this map can be regarded as 3 rotation counterclockwise by pi over 2 or 90 degree. So you can think of this as a rotation followed by a rotation followed by a rotation, and this can be denoted as r cubed. And so r cubed is going to be a map, again, from the vertices of the square into the vertices of a square, where so 1, where is 1 now? 1 is in the 4th corner. What about 2? 2 is in the 1st position. 3 is now in the original second position, and then 4 is now in the 3rd position. So that's what we have. Now what happens if we rotate the square by around the origin, again counterclockwise by 360 degrees? Okay, now what happens if we rotate 360 degree counterclockwise? Well, let's see. Rotate 360 degree counterclockwise. Nothing. We get again the same configuration. All right, let's write this down. Okay, so a rotation by 360 degree counterclockwise around the origin is essentially four rotations by 90 degree counterclockwise, and we see that if you compose R with itself 4 times, we can rewrite this as R power 4, and that's essentially the identity map. And what is the identity map? Well, the identity map is the map from these sets into itself, which send every element to itself. So 1 goes to 1, 2 goes to 2, 3 goes to 3, and 4 goes to 4. Okay, so far we have constructed the identity symmetry. We constructed R squared, and then R cubed. So far we have 4 rotations, 4 symmetries. So are there any other symmetries? Well, yes. Let's look at the other one. Okay, so we can also reflect with respect to the first diagonal, which we denote here by D. So let's see this here. So we'll reflect the square and then you can see what happened is that so by reflecting around the first diagonal, we are essentially fixing 1, because 1 goes to 1, 3 goes to 3, and but now we'll swap 4 and 2. So 2 now is in the 4th position, and 4 is in the 2nd position. We'll call this symmetry D. Okay, we can also reflect through the 2nd diagonal, which we label here by A. So it will be this line here. This is the 2nd diagonal. If we reflect through this line, let's see, so we select and then we reflect to the 2nd diagonal. You can see that 2 and 4 are fixed, and then 1 and 3 are swapped. So let's write this down. So through this reflection, what happens is that, so we have 1, 2, 3, 4. 2 and 4 will be fixed, right? So 2 goes to 2, 4 goes to 4, but we'll swap 1 and 3. So 1 goes to 3 and 3 goes to 1. Okay, so far we have what? We have the identity map, we have R, we have R square, we have R cube, we have D, and then we have A. I claim that there are 2 more symmetries left for us, which are distinct from these first 6 symmetries that we have studied. So let's look at them. We can also reflect through the x-axis, and let's see what this will entail. So we will reflect the square through the x-axis. All right, so let's write down what we just observed. So what we saw through this motion is a map which we'll call x, and this map is now sending 1 to the 4th position, right? And what happens to 2? 2 is now in the 3rd location. What about 3? 3 is now in the 2nd location, and then 4 is in the 1st location. And finally, we can reflect through the y-axis. So this is done as follows. So reflect through this y-axis, and let us write down what we just observed. Okay, so through this map, what we observe is that the first vertex now is now located in the 2nd corner. The 2nd vertex is now located in the 1st corner. The 3rd vertex is now located in the 4th corner, and the 4th vertex is now located in the 3rd corner. So essentially 1 and 2 swap, and then 3 and 4 swap. And so this gives us what? So far we have the identity, we have a rotation counterclockwise by pi over 2, 2 of those rotations, 3 of those rotations, a 4 rotation counterclockwise by pi over 2 gives us back the identity. We saw D, reflection through the 1st diagonal, reflection through the 2nd diagonal, and reflection through the x-axis and reflection through the y-axis. I claim that this set here is in fact a set of all symmetries of the square. All right. Okay, I will now do a little bit of relabeling that will allow us to keep track of all of the different symmetries that we have. So far we have the identity, symmetry, and we'll denote this by E. We have the rotations, R, I'll call it little r, R square, and then R cube, and these are counterclockwise rotations by 90 degree, 180 degree, and 270 degree respectively about the origin, or respectively. Okay, we'll call T A C. This is the reflection about the diagonal AC. We'll call TBD the reflection about the diagonal BD, we'll call T X the reflection about the x-axis, and we'll call T sub y the reflection about the y-axis. So you can then say that I claim, so this is a claim, it's not a proof yet, so let me write it down. So the claim here is that the set of all symmetries of the square A, B, C, D is given by the sets containing E, R, R square, R cube, TAC, TBD, TX, and TY. And I claim that this is all. So we have a total of 8 distinct symmetries of the perfect square. Now, the best way to see whether our claim is true is to actually look at this composition table. So if we take the identity map and we compose the identity map with the identity map, we of course expect just the identity map. If you compose the identity map with a rotation, you just get the rotation, right? Same with 2 rotation, 3 rotations, translation, reflection with respect to the x-axis, reflection with respect to the y-axis, reflection with respect to the diagonal AC and diagonal BD. So that will be the case, and similarly here we'll have R composed with E is going to be R square, R cubed, TX, TY, TAC, and TBD. Okay, now if we compose 2 rotation, we get R square, right? R composed with R square is going to be R cubed. R composed with R power 4, we saw that that's actually the identity, so that will be E. Okay, so now we have come to a point where, let's see, and maybe you can still do some of them, right? So if you take R composed with R square, R composed with R square composed with R will be R cubed. This should be the identity. R cubed composed with R will be the identity. R cubed composed with R square, let's think about this. This will be, so R cubed composed with R square will be R power 4 composed with R, but R power 4 is the identity composed with R, so that's just going to be R, right? R square composed with R power 5, again it's going to be R. If you take R power 6, I'm sorry, R cubed composed with R cubed, what you get is going to be R power 4 composed with R square, and that's going to be E composed with R square, which is going to be R square. Okay, now we have come at a point where we need a little bit more information to fill the rest here. Okay, so let's look at this map here. What happens if we compose, if I take R square composed with reflection with respect to, I'm looking at this one here, take R square and then we compose it with reflection with respect to the x-axis. What do we get? Let us go back to our original diagram here. Okay, so let us first apply reflection through the x-axis. So we'll take this and then we'll reflect through the x-axis. Okay, now we will rotate counterclockwise by pi over 2. No, by 180. Sorry. So we get this configuration here. We get a configuration of this type where we'll have 1, 2. So originally we have 1, 2, 3, and then 4, right? But now, after we perform these symmetries, now we have here 1, 2, 4, and then 3. Okay, so let's see what happened. If I start with the square 1, 2, 3, 4, and then we apply a reflection about the x-axis, then we get this configuration here. And then if we follow by rotation counterclockwise by 180 degree, then we get this configuration here. And you notice that this is essentially just a reflection about the y-axis. So r square composed with tx is going to be ty. Now let us try to understand what is r square composed with ty. What is that equal to? So if we take r square composed with ty, we get tx. Notice, again, we start with the square here, right? We apply ty, we get 1, 4, 3, 2. We apply r square, and we get 1, 4, 3, 2. And that's a reflection through the x-axis. So r square composed with ty is t. We just proved that r square composed with ty is tx. I would like you to try to prove that if you take r square composed with tac, you will get tbd. And if you take r square composed with tbd, you get tac. So r composed with tx is going to be tac. R composed with ty is going to be tbd. R composed with tac is going to be ty. R composed with tbd is going to be tx. And r cube composed with r cube composed with ty is going to be tac. This will be tx. This will be ty. This will be tbd, tac, tx, ty. This will be ty, tx, tbd, tac. And you can see that you can fill the entire table by playing the same game that I've shown you. And you can see that you get nothing new by taking any combination of the 8 basic symmetries that I've shown you earlier. Right? So that's it. We have proved that the set of all symmetries of a square consists of the elements E, R, R square, R cube, tx, ty, tac, and tbd.